So now we're going to talk about some couple of algorithms using these Q and value functions. So first algorithm is called policy iteration. Let's talk about this first. This policy iteration algorithm is composed of two steps. First step is policy evaluation, and then the second step is policy improvement. Let me first talk about policy evaluation. It's actually just I mean, not even very, it's exactly same as the example that I showed you previously. So at time equals t, we initialize the value functions of each state as zeros. And then if we calculate um, this part, it's going to be because we have four possible directions, and we'll initialize the state transition probability equally. So 1 over 4, 1 over 4, 1 over 4, 1 over 4. And then it's going to be 1 over 4 times reward. So if it is boundary like this, we assume there's a dummy function, and the reward is 0, and the value is 0. And then your position still will be the same state. The point here is that even if your next state is the same state as before, if you move up, you don't want to use the value from this current state, but the value from the dummy state though, because it's boundary cases. So your value reward is 0, gamma times 0 is just 0, plus 1 over 4. Then for the same reason it's boundary dummy, so it's 0. And then 1 over 4 again if you move down, and you have finally something non-zero reward, which is negative 1, plus gamma times 0. And then 1 over 4, 0. So it's eventually going to be negative 0.25. So at t plus 1, your state value will be negative 0.25. That's it. And you do the same for the rest of the cells. So if we look at this cell, you have all these neighboring, three possible neighboring cells, and their rewards are 0, and their respective values are 0. So all zeros. So no update. It's still 0. And same reason for this cell, 0. And for this one, this state at t0, we have this one neighboring good reward cell. So it's going to be uh, 1 over 4 times 1 plus 0, 0, 0. So positive 0.25, and that is negative 0.25 because we have neighboring cell as negative 1. And then for the same reason here is positive 0.25 and negative 0.25. And already we can see some kind of tendency here. So right after the first iteration, we have some values like this. And if you want to use the greedy algorithm, you choose higher expected value. So you want to choose 0 because negative 1 is smaller than 0. So we want to choose this direction, and then negative 0.25 and 0, and 0 is larger than this one. So we want to go there, go there, go there. This that's it. I think that's the basic idea of this policy evaluation. And I have this one, but well, you keep doing the same thing. So far, we have been updating the state's value function, and now say this is t equals some time t, small t, and then at that time, let's say this state's expected value is somehow, I don't know, 5, and reward value is still 0, and then that cell's reward is negative 1, and then expected value is, I don't know, if you choose to update, say that's negative 3 or something like that, then we said we're going to use the greedy algorithm, and we have 4 possible actions with 1 over 4 probabilities as an initialized value. And then we calculate this sort of value function again. So if we choose to move right, let's write somehow like this. So if we choose to move right at state S and action is R, and then our value function will be 0, which is reward, plus discount factor times expected value of the next cell, and that is times 5 is 4.5. And then if we move up or left, it's just going to be zeros. Up or left will be just 0. And then if we finally choose to move left, move down, and that value will be -1 plus gamma times -3, and that is minus 9/10 times 3, and that is -3.7, I think. Is that right? Yeah, I think. So so we will look at all these expected value, and this is actually a Q function for each direction, and we choose the highest one. Then in this case, this one's value is the maximum, so what we're going to do is divide, well, not divide, I'm sorry, we are initialize the probability as 0, and we're going to choose only maximum 1. So next probability will be 0, 0, 0, 1, because moving right is our fourth element. So next time t plus 1, it'll be 0, 0, 0, and 1. So the probability of moving right is 1, so your agent will always choose to move right in this case. But say after this kind of calculation for another state, let's say we happen to have these Q values as Q values are like this, 0, 0, 0.5, 0.5. So you have same expected value for each two of 4 directions. Then in this case, what we're gonna do is for the probability update, we're gonna do 0, 0, 1 over 2, 1 over 2, and that's because we have two same maximum values. So number of maximum value is 2 because they're the same numbers. So our new probability will be 1 over 2. So if we can generalize, if we have n number of maximum values, then the probability just will be 1 over n, and we will assign this n, 1 over n, to the corresponding index where this maximum Q values have.